about stability foliation is Florian. Stage is yours.
Thanks for the introduction. Give me a second. Okay, thank you very much for the introduction and for the invitation to speak here. The sound works. Okay. Yeah, it's a great pleasure to be here. It's my first time in Brazil, so many new experiences. And from a personal stage, I'm really, I felt, despite all the rain, I experienced a very warm welcome here. So I'm very appreciative of this and all people who are involved. So thanks a lot for that. And so today I want to talk about some stability results for foliations, and in particular a joint project with Stefan Goedens, who is a postdoc at the University College in London. Right, and I don't know, as it happens sometimes in math, you have some idea which you want to work on, and then you wander off into the wild trying to understand, and then you end up somewhere completely different. So we actually started by, we wanted to understand the deformation problem for co-isotropic submanifolds and symplectic manifolds. And there you have the today local model, and so locally you can understand them around the co-isotropic submanifold by looking at the T star f, for f being the characteristic foliation. Right, and so basically close enough co-isotropic submanifolds can be understood to first order in terms of closed foliated one forms, and that's how we got into trying to understand how we can solve the deformation problem there, and that's how we got into foliations. And then when we searched for a homotopy operator for this cochain complex, we discovered that we can actually use them to prove also something about foliations, and that's really how we ended up with this type of project here. Right. So I roughly have structured my talk in 3 parts. The first will be the definitions which we need to state the results. Second part is results which are known in the theory and what we have proven. And then the third part will be talking about the proof, basically. Right, okay, so let's jump right into this. The definitions. And so, so M is a smooth manifold here always. And I want to start very basic. So for me, and at least for the purpose of this talk, I consider F a foliation of dimension K. And if we have, a k-dimensional subbundle of the tangent bundle, such that, if we look at the sections, we have a Lie subalgebra with the section restricted to, with the Lie bracket restricted to the sections. Of the vector fields on M. And okay, so the first thing I want to define is what does it mean to be stable for foliation. And for this, we actually want to understand foliations as a subset of a space where we have topology on. And so the standard way to do this here is to understand k-dimensional vector bundles as sections of the Grossmannian bundle. So we have the Grossmannian bundle, k Grossmannians over M. So maybe as a reminder, the fiber here, at the point X would just be, some vector subspace of Txm of dimension K. And so in particular, we can understand foliations of dimension K on M as a subset of the sections, the smooth sections of this bundle. And so on the smooth sections, we have a natural topology, the C-infinity topology. And so the way we topologize our foliations will be by just implementing the subspace topology correspondingly. Okay, so that's one part which we need. So we obtain the topology on the foliations. And The second part which we have here is if we have a diffeomorphism on our manifold, right, that naturally acts on the space of foliations by just pullback with respect to the diffeomorphism. Right, and so these two combinations give rise to the definition of stable foliation. So we call the foliation F stable. Right, so if we can find a neighborhood inside our topological space, the foliations of F, such that for every foliation in there, for every F tilde or F prime in V, we can find the diffeomorphism mapping F prime to our original foliation. Right. Okay. So now that we have defined stability, what I want to do next is I want to understand what stability means in terms of first order approximation, or in other words, what is the cohomological condition for being stable. Right, so that is what we call here infinitesimal stability. Right, and so let me first briefly explain the cochain complex we're looking at. So given a foliation, we naturally have associated the bot connection on the normal bundle. Right. So that's a map from the sections of TF times sections of the normal bundle. So this is TM quotient out by TF. Oh, that was too much. To the sections of the normal bundle. And it's defined, well, the way you might think of it is, so we have a section which is tangent to the foliation, a representative for a section of the normal bundle, and we map it taking the bracket with respect to the representative and then taking the class in the normal bundle. Right? And so we can use the bot connection to define a differential on foliated forms with coefficients in a normal bundle, which I denote like this, and the corresponding differential induced. Well, this is a flat connection, so we get the representation on the normal bundle, and then we get a cochain complex. Using standard formula. And correspondingly, we get the foliated cohomology with coefficients in the normal bundle. Right. The corresponding cohomology groups. Okay. Right, so what we want to understand is infinitesimal stability. So in order to understand this, we look at, let's say, one parameter family of sections inside, let me write it here, inside the sections of the Grassmannian. And right, so essentially if we have a vector space and, well, a vector subspace, and we want to describe some vector spaces which are close enough, we can always model them locally by a map from the vector space to the transverse vector space. And so we can realize this for small enough epsilons as the graph of some, let's say, psi epsilon or psi epsilon, one form, foliated one form with coefficients in the normal bundle. Right, so we think of TF as our vector space, we have the normal bundle, and then everything which is close is basically modeled as a linear map in between them. Right, and so Now we have two conditions. So first of all, if we assume that this family describes actually a foliation for the corresponding epsilons, and we assume some smoothness assumption with respect to epsilon, what we obtain is that if we take the corresponding derivative of this foliated one form at epsilon equal to 0, then this gives us a co-cycle in the foliated one forms with coefficients. So that's the first condition which we obtain. And the second condition is if we actually have an isotope, right, so maybe one thing to say, we always start at our fixed foliation f at 0. Right? And so the second thing which we can actually observe is that if we have an isotopy for all the epsilons, then we actually can say even more of this. So family such that psi epsilon, put back f epsilon, is f. That implies that this corresponding cocycle is actually a coboundary. Is a coboundary. Okay, and this results by Heitch in the year 1975 or something. Or Chuck, where did that? Yeah. Right. Okay, and this kind of motivates the question of the definition of a foliation being infinitesimally stable. Namely, we call it infinitesimally stable if the corresponding cohomology group H1 of f with coefficients in a normal bundle is vanishing. Right, and so basically the purpose of this talk, or the goal for everything we are doing here, is to prove results along the lines of, given that we have a foliation which is infinitesimally stable, can we show it is stable? Are there any questions about this part?
This condition of stable is open and dense, something like that, or is very special, very specific?
The cohomological condition, you mean?
Foliation that is stable is a very...
Yeah, I guess most foliations you encounter will not be stable, if that's the question.
Okay.
Right, that's a way to think about it.
Okay, okay.
Right, I only talk about regular foliations, right? Okay. Right, so then let's talk about some results. Right, so there are a couple of results in like the literature which I want to mention here. So the first one is by Hamilton, which is actually something which is unpublished, which states the following. So we have our manifold which is closed, our foliation which is Hausdorff, and so what this means in this case is, right, since M is closed, the leaf space M quotient out by equivalence classes of being in leaves is compact. The foliation being Hausdorff means that the quotient space, the leaf space, is Hausdorff, and that in turn means that we have a foliation by compact leaves. So that's in this case. And for such foliations, well, it is well known that all the leaves have finite holonomy, and actually most of them have trivial holonomy, and most of them means there is an open dense saturated set of leaves with trivial holonomy. That's what's called the generic leaf, and the assumption here is that the corresponding first cohomology of the generic leaf is 0. Right, so, and H1L, or L0 is 0 for L0, the generic leaf. And the statement is that if this holds, then the foliation is stable. Okay, so now this result is unpublished, and the reason for this is that around the same time, Epstein and Rosenberg proved actually something which is significantly stronger. Namely, right, what did they prove? They showed that if you have a manifold without boundary and F being compact Hausdorff, so they don't assume any compactness. Sorry, they don't have any compactness assumption on the manifold. They only have the assumption that there is no boundary. So in this case, just being a Hausdorff foliation is not enough to have compact leaves. So that's why they require it additionally. So it's very similar to this one. And their statement is compact Hausdorff CR foliation. Right, so they treat the CR case for R being bigger or equal than 2, I think. Okay, so I think bigger or equal to 2. And the similar assumption then F is CR stable. Right, meaning that you do not find like, yes. Right, yeah, that's also something, yes. Right. So you still have the generic leaf and you still require that to be vectorial cohomology. Right. Okay. And then maybe a third result I want to mention here is, right, so I think that was in 1977. And then another result which is basically along the lines of Hamilton, which is by Matías del Hoyo and Rui Fernandez. Which, well, essentially it's the same statement as here with a slightly different notion of stability. And the difference there, which I will explain in a second, and the difference there is that they prove it using very different techniques. So we will talk about the result and the way Hamilton proves this in a second, since we also use it for our result. The way Matías and Rui prove it is basically they realize foliations in terms of deformations of Lie algebroid with some specific property, and they use rigidity of corresponding Lie groupoids and show that this actually implies this result as well. Right. Right. So maybe let me just write similar as Hamilton. With a different notion of stability. Right, so in their case, they don't consider like stability the way we define it here, but they consider only deformations of foliations which are controlled by like a parameter. So the right, so connect they are path connected to where you start from, and then they require for it to be stable and isotopy actually to do this. Right, and so well, in their paper they actually mentioned that the exact relation between those two is something which will be explored. It has not been yet, so we'll see. Right. Okay, so that are this, right, and that's very recent, that is like 5 years ago. Okay, and then we have our result. Which states the following, namely if M is closed and F is Riemannian, which I will recall in a second. Right, F closed, F a Riemannian foliation, and it is infinitesimally stable, meaning that the first cohomology group vanishes, then F is stable. Right. Okay. Right, so maybe first let me recall what the Riemannian foliation is. We have seen this already in the last talk yesterday. There are different ways you can think about that. Yesterday we have seen the definition of like having a bundle-like metric. In the literature there's also the notion of having a holonomy invariant metric. Or you can understand it as a metric on the normal bundle which is flat with respect to the bot connection. So all the three things are same. Okay, and we also have seen examples yesterday, so that's very good to have some understanding of what it is. Right, so that's our statement. Now, right, so in my abstract I wrote that this is potentially a new theorem. And the reason for this is that we do not exactly know yet how it fits into, well, basically how it fits with this result over here from Hamilton. The point is our result certainly implies the result by Hamilton, but it's not so clear if they're actually different. So, right. So the question we actually raise is, are there Riemannian foliations such that they are infinitesimally stable and F is 0, but they are not of this form, right? Let's say they are not Hausdorff. Right, so yeah, I don't know, like we proved our nice theorem, we were very happy, we tried to understand the differences. Well, we saw it's not so easy to understand the differences, basically. Yeah. I mean, so once, right, we are also in a closed manifold, so once you know the foliation is Hausdorff, you know it has compact cleaves. And so that means you know that it has a generic cleave. Right. Is that the question?
And then you also know that the infinitesimal stability implies that the H1 is
you have a cohomology relation. Yes, I think so. If I'm not, right. Right. So we were searching a bit, and basically we have our paper written, except for we do not understand this question. And we tried a couple of cases, and then we actually found a paper which answers this question partially. Which is due to Etienne Guise in, I guess, 85. And basically it says, if M is simply connected, then the answer is no. Right, if M is simply connected. Right, which is, yes.
Which implication you're saying is clear between these two results?
Right, so this theorem implies this one, because basically what you can do is you have here the generic leaf, and you have a very nice local model around every leaf from Rabe stability, and that allows you to build this Riemannian metric locally, and you can see it glues together nicely, so you get this kind of condition. And so, right, you can apply this theorem for this one, but it's not clear if you have a foliation like, right, if you have a foliation which does not satisfy this condition, but which fits in here. Right. No. Right, I mean, you have there is some proof behind this. Right. Okay, and right. So basically, F being Hausdorff means it has compact leaves, and right. So basically, what this means is that you can understand the leaves very well. So for every leaf, you have a well-described local model, which is given by local wave stability, basically. And so that means around every leaf, you can, in a saturated neighborhood, you understand very well what's happening. And on these neighborhoods, you can define your Riemannian foliation, your Riemannian metric by hand. And then you can actually show that this glues together to a Riemannian metric on everything. Right. Okay. So yeah, that's about where we are at the moment. And so, if you feel like you don't want to follow the proofs, maybe that's a question to think about for the remainder of the talk. If anybody has some idea, I would be very happy to listen to the ideas. Right. Okay, so that's one part. And then I want to remark that there are stable foliations which do not fit into this framework. So there are definitely stuff which we do not cover with our theorem. There are, that's not what I want to write. There are stable foliations which are not. Riemannian, and okay, so there we have the first example was given by Gies and Sergius. And then, right. Okay, just to do people justice. Okay. Right. Okay, so far the results we have, and right, if you have questions, that would be a good time. Otherwise, I will move on to discussion of a proof of the statement. Sorry? Yes, so I think, right, so there was first one example by this guys, Gies and Chasiesco, and then these people, they generalized it. And so what they have is basically they take some n torus and you act on it by some integer valued matrix, like let's say SLNC. And so what you do is you define like a linear foliation on your n torus, a k-dimensional, let's say. And then if you, right, so you want the matrix you choose to have certain properties with, well, the eigenvalues should have certain properties with respect to like the tangent generators of the foliation and like the transverse generators. And what they then do is they take the suspension foliation, and because of the special properties of the eigenvalues, they can show that it's not Riemannian, and then they prove by hand basically that it's stable. That's kind of right. Okay. More questions? Good question. I don't know. I don't know. Yeah, I will go into like well, Molino theory in a bit. And maybe I explain a bit what like issues might be there. But yeah, let's keep it in mind maybe, and otherwise talk afterwards. Right. So part 3 would be proofs. Okay. Right. And so for the proof, Right, so our theorem is really very much related to the statement by Hamilton, so much in the sense that Hamilton has like one of like the main theorem which implies stability, which we use as well, but then the way we obtain the how do you say, like the preliminaries to satisfy the statement, we like prove them in a different way. So that's why I first want to talk about Hamilton's stability theorem. I don't know, that's how we call it. Right, I need some prerequisites here. Right, so we fix our closed manifold, our Riemannian foliation, and the bundle-like metric. So closed manifold, Riemannian foliation, and G a bundle-like metric. Right, and right, so we do this to define an inner product on foliated forms with coefficients. So we define, I guess, alpha times x and beta times y. We define the inner product here by integrating over our manifold, taking, I guess, the co-metric on the forms and the metric on the normal guys. Right, so here alpha tensor x and beta tensor y, we think of them as forms on F with coefficients. Well, since we have a bundle-like metric fixed, we realize the normal bundle as the orthogonal complement of the foliation. Right. Okay, so this defines an inner product, which we need for the following statement. So, right, so we have the same preconditions, MFG as above. And then we have this analysis estimates. So if there exists some constant such that for all forms, foliated one forms with coefficients, I guess TF normal, we have that the corresponding norm of eta can be bounded by C times. Okay, I see you have a place problem here. Right, so basically what Hamilton does in the theorem is he translates the property, this cohomological property, into like what he calls a weak cohomological property in terms of an analysis estimate. And so here d nabla is the corresponding differential on the foliated forms with coefficients induced from the Bott connection. And then we have here an inner product, so this delta nabla is just the corresponding the co-differential with respect to the product. Right. Okay, and since we rely on the statement, I also briefly want to go through the idea of the proof of this statement. I guess proof idea. Right, and so the situation looks a bit like this, right? We have our foliated forms, so zero forms, to one forms, normal to two forms. That's really all we are interested in. And so here we have our differential, and then we have the co-differentials in the other direction. And so basically, right. So using the differential and the co-differential, Hamilton proves that this estimate here, which I should denote by star maybe, implies that the corresponding Laplacian is invertible. Let's say with nice estimates for the moment being. And so, right, having this Laplacian being invertible, he defines cochain homotopy operators H1 and H2, which are tame, right? So I should say these estimates are maybe tame, what I call here nice. So there exists H dot, as pointed out here, such that so X can be written as right. We have d nabla composed with H1 of X plus the other way around H2 composed with d nabla of X. Right. So basically, if we start here, let's see. Right, so if we start here and we go down with H1 and up again, plus going first up and then down, we end up in the identity. So that's one condition. And the second one is the tame estimates. So that means just that if we estimate H1, H2 applied to, let's say, beta dot, the nth norm of it can be estimated by some Cn and n plus dth norm for some fixed d. Right. So here the dot stands for 1, 2, depending on where they are defined, and this is what is called tame estimates. Right. And so having this cochain homotopy operators which satisfy these estimates allows him to apply a Nash-Moser type argument to construct the diffeomorphism, mapping the foliations to each other. Right. Okay, so that's the rough idea of this proof. And so now the difference between the proof of Hamilton and the proof we have is how to obtain this beautiful looking estimate. And so, right, so the way Hamilton does this is he uses these nice local models around the compact leaves, and then basically he shows this and that you can satisfy this estimate in every local model, and then that it is actually satisfied that way. Right? And so we actually, in contrast to this, we do not go to the local model, but we use what is called Molino theory for Riemannian foliation, which I want to describe next. Right. Right, let's say Molino, yeah. And so, right, our starting position is the same as before. MFG, a closed manifold, a Riemannian foliation, the bundle-like metric, and right. So what do we obtain from this? Well, we can form the transverse orthogonal frame bundle. So I told you that the bundle-like matrix basically is a special metric on the normal bundle, and that gives rise to the, well, to having first of all the transverse orthogonal frame bundle, which I call M hat, over M transverse frame bundle. Right, so that's an OQ principal bundle, where Q is the codimension of the foliation. Codimension of F. Right. And so the nice thing about this transverse orthogonal frame bundle is that we can actually lift our foliation to a foliation of the same dimension upstairs. So, right. So we have this F hat foliation on M hat, where two elements E in M hat X and F in M hat Y are in the same leaf. Right, so if, well, first of all, the base points X and Y have to be in the same leaf on the base manifold. Right, and then that is one condition. The second condition is if we have a path, well, we take a path between from X to Y and leaf, and we want to the corresponding linear holonomy to map the orthogonal frame E at X to the orthogonal frame F at Y. So basically, every leaf will be a holonomy of the leaf downstairs. Beautiful. Okay, and now, since our time is limited, let me just write down a couple of properties. Yes. Right, so a couple of properties. So first of all, this foliation will be invariant with respect to the action. Right, so the projection from M hat to M, it maps leaves to leaves. And as I just said, if we restrict it to one such leaf, then this is just the holonomy cover. Right. Okay, and so what's really nice is that if we actually lift it upstairs we can always trivialize the normal bundle. So basically that allows us to reduce the study of Riemannian foliations to those Riemannian foliations which are transversely parallelizable. Right. So we have a natural identification of the normal bundle on F with the Lie algebra OQ plus RQ via omega and theta. So theta is here like the canonical one form on the frame bundle, and omega is, well, in terms of forms, a transverse Levi-Cicci-Vita connection, or like a connection one form for the corresponding orthogonal bundle, transverse orthogonal bundle. Right? 1, 2, 3. There's something else I want to say there. Right. Okay. Right. Okay. And so, right, any foliation which has a trivial normal bundle is naturally a Riemannian foliation, so the foliation upstairs will also be Riemannian. and the corresponding metrics are compatible. Right. And so we want to do analysis with this, and so we have the following maps which are important to us. So we have the foliated forms with coefficients on the base. We have an inclusion. What is the inclusion? I guess the inclusion is pi star. Two foliated forms on the lift, and here we have the corresponding pullback bundle, I guess. And the nice thing is, because upstairs the normal bundle is trivial and also the corresponding connection is very nice, we actually can identify these forms just with foliated forms. Times the codimension, I think. Right. And so this map here is not only an inclusion, but in fact one can choose the metric upstairs G hat in a way such that this is an isometric inclusion. Right. And so in particular, we can make this an isometry if we restrict upstairs to forms which are invariant under the OQ action. Okay, and so that is all the preparation I need to outline the proof of this gorgeous estimate over there. Are there questions at this point? Okay, great. So, right, to the proof of start. So we do a proof by contradiction. We assume we have a sequence such that the corresponding norm is normalized to 1, and the corresponding norms for the differential and co-differential they are going to 0, so that we cannot satisfy our estimate over there. Right, so what we do is basically the following. We take the sequence, we use the corresponding isometry where we use the invariant forms here, we lift it upstairs. Upstairs, we can identify them with just standard forms. We find an extension to the manifold itself. And then on the manifold, we apply, well, there is a result which basically, right. Maybe let me first make the statement before I continue with my elaboration of something which does not make sense yet. So the claim is that there exists a converging subsequence which converges to an element in the kernel of the Laplacian, but then in the L2 closure. Right, and so now I continue with my elaboration. Right, so we have the sequence, we lift it upstairs, we trivialize it, we extend it to a sequence of standard de Rham forms on M hat. And for standard de Rham forms, there is such a statement which basically implies literally this. And then we map it back downstairs, the corresponding limit, and that gives us our limit here. So that is roughly what's going on without writing out the details. Right? Okay, so that's one part. Yes? Good question. Let me check. No, it is 1C for all eta, if I did not write my... Yes. Right. Okay, so that's the first part. And so we want to bring this to a contradiction. So we want to do this by showing that this has to be 0. And for this, we used the result by Alvarez-Lopez and Kodyukov, who proved that for Riemannian foliations, we actually have a leafwise Hodge decomposition, which is very nice. Right, so M, F, G as before. Right, a leafwise Hodge decomposition, but not for the foliated cohomology of coefficients, but for something slightly different, namely the cohomology H bar of F, let's say TF normal, which is defined to be the kernel quotient out by the closure of the image. Right, so, and right, for leafwise cohomology, like being closed is not as natural as it is for the RAM cohomology, so we have to be very careful what we're doing. And so the statement is that for this type of cohomology, there exists a leafwise Hodge decomposition. We have a leafwise Hodge decomposition. Hodge decomposition. All right, I'm almost done. Write the correct statement. Right. So we have for the forms, we can write them as the kernel of the corresponding foliated Laplacian plus the image of the foliated Laplacian. So here we have the C infinity closure, because just to not confuse this, I guess this should also be C infinity, correct? And so this is the kernel of the differentiable intersected with the kernel of the codifferential plus the image of D nabla closure plus the image of delta. Right. And so what this means for us is, in particular, means that H1 bar F and F is equal to the kernel of nabla. Right, that's what I want to write. And so, right, that's the statement. And now we use this to conclude our contradiction. So conclusion. So H1, the infinitesimal stability, let's write TF, implies that this, well, closed version of it is 0. Which means that the kernel of the Laplacian is 0. And so is the corresponding closure, and so alpha has to be 0. Okay, and that finishes the proof. Okay, so that's the proof. Right, and I think I will stop here. Thanks for your attention.
When you define stability, you don't take into account that you're going to work with manipulations.
Right.
So you could, for example, put that into the group. So instead of looking at the difficulties in the group, with it. If you already have the metric, you can look at the group of isolation
Right.
active on this. And you can also look only at those distributions. Which will give you can look at only deformation by remaining locations. Like, in a sense, you get a smaller group, but you also get a smaller space for your act.
Right.
It could be a chance that your theorem would still hold it this second. Then you'll get like stability for like really for remaining foundation under isometries.
Wait. So you're saying, right, so you act with a smaller group on Riemannian foliations. So that would imply, right, so those who are stable have to be still stable.
No, not, right? Because I mean, they might be stable under a different field, which is...
Right. Oh, I see.
But you also allow less foliations.
Right. I mean, that's like, I mean, I never looked at it. I guess my answer would be maybe. I don't know. Right. It's an interesting question. I just don't have no feeling for it.
Other questions? Comments?
Yes.
Yes.
So in this paper, Matthias and Bumi, I think they use a different perspective, right? They construct using exponentials and so on. Do you think this could also be adapted in that way? Like in a group way, kind of.
Right. So I mean, I think the use. I mean, I don't know the paper exactly, but I think they use compactness of the leaves to some extent to like say something about groupoids or the algebroids and integrating them. I'm not sure how you would do this if you do not have the compactness. I think like you would need to see if there's a way around the use of compactness for this type of thing, and what you would get maybe. Yeah, I think it depends on that part.
Other questions or remarks? Again? Carvalho, who will speak about modification of Poisson structure. Please, Pedro.
Okay, thank you. So first of all, let me thank the organizers for the invitation to speak. It's very nice to have this opportunity. The last time that I attended one edition of this workshop, it was the edition that took place in São Carlos 5 years ago, and I was a master's student there, first year. So it's very nice to be here and to give this, to give my contribution to this edition. So yeah, so I'm going to talk about homological reduction of Poisson structures. So this is also the title of the paper that I posted on arXiv around 3 weeks ago or so. So the presentation will be essentially based on the content of this preprint that's there, okay? So let me just briefly explain what I want to say here today. It's essentially summarizing this picture. So maybe, I don't know if you know, but what homological reduction is really about. So I want to explain what exactly I mean by homological reduction. And I will start the context in the usual Hamiltonian context. So you have like a G action on a Poisson manifold with a moment map, and you do something, this homological reduction, and you get a differential graded Poisson algebra that knows something about the reduced space associated to this reduction data here. Okay, so, and this is, this differential graded Poisson algebra here is what Constance Steinberg in their paper call actually BRS algebra, and there's also sometimes appear with a T in the literature. Okay, so what I want to say, so I will start by this to explain to you what I mean by homological reduction. Okay, so, and what I want to do here today, my idea is to explain to you how can you generalize this to this more general setting here, when instead of having like a map that takes value in the dual of the Lie algebra, you actually have a map that takes value in the, the dual of G module. Okay, so it's a bit more general. And when you do essentially like you apply like this homological, the ideas of homological reduction, you get something more general, which is now homotopy Poisson algebra, which is also known as p-infinite algebra or zero shift Poisson algebra. Okay, so I want to say that this kind of setting here appears like when you kind of interpret Poisson reduction in terms of graded, in terms of graded geometry. So as I will explain, this kind of setting here, where is it here, appears when you look at Hamiltonian reduction of the shifted cotangent bundle. So when there is a non-graded interpretation, yes. H star, it's a G module. So you have an action of G on a G module, and you have this equivariant map. So it will be clear that there is a correspondence between these kind of things here and some kind of graded actions on the shifted cotangent bundle where you see this Poisson structure as a function. So I will explain that, okay? So let me say what I mean by homological reduction in this context, in this Hamiltonian context, the usual Hamiltonian context. So the idea is that you have like a space, you want to take this reduction data, you want to construct something that knows about the reduced space. So I'm interested in function of the reduced space. Okay, so the idea is, let me kind of a description of the functions on the reduced space. So we start with the usual reduction, Hamiltonian reduction data with a G action with a moment map. You know my Marsden-Weinstein theorem that we have like this other Poisson manifold, right? So you look at the constraint submanifold that's given by taking pre-image of the zero, and you model out by G, and you have like this reduced space. So what are the functions on this reduced space? So if you denote by C, the level set, and C red, like the reduced space, we have that functions on the reduced space are actually functions on the constraints to manifolds that are invariant by the action, right? So functions that are constant along the order. And if you denote by I, the vanishing ideal of this constraints to manifold, which in this case is actually this I is actually the span of taking like the pre-image of you see like this, you know, for example, take a basis for the Lie algebra, and you see the functions on the dual, and you pull back this, and this here will spawn for you this ideal, okay? These functions. And because this map, I forgot to write something here, but this actually, I should have written something like that. Okay, so this ideal is quasotropic because this map, because of the fact that this map is, okay. So, and functions on the on the constraints manifold is actually the same of taking the quotient by this vanishing ideal, right? So, and the invariant functions happen to be isomorphic to this thing here that's called the normalizer, which is defined here. So it's essentially all the functions that when you take the bracket with the generators of I, you are in I again. So these invariant functions here can actually be identified with this. And because of this condition here, this thing here is actually a Poisson algebra, has a Poisson bracket, and it's actually isomorphic to the Poisson used by vector. Okay, so this is here for you a way of talking about reduced functions without talking about the reduced space in some sense, because everything here is defined in terms of function on the whole manifold. Okay? Right, so the homological model that I want to describe here comes out of realizing this restriction. Taking variance logically. How can you do that homologically, right? So for the restriction part, this C complex. For the restriction part, you consider the so-called Koszul complex. The same. So you have these functions here. So the map from here to here is defined by taking this I to the corresponding constraint, right? And here it's defined by 0, and you extend it as a derivation of degree -1. Okay. As a degree as a derivation of degree 1, because you see this as something in degree -1 and goes to something of degree 0. Okay, and this is a resolution of this quotient. So I don't have higher homology. Higher homology. All the higher homology groups vanish. And for taking variance, you can see that here we have actually a G modulo. So we can take the corresponding Chevalier-Lemberg complex, right? So we take like, you know, this Gx here by the adjoint action and X here because we have an action. So you just consider the corresponding Chevalier-Lemberg complex, okay? So the BRC complex is the total complex of this. So you have these two differentials, and you consider the only total complex. So you define this grading here. This grading, it's called like total Gauss number, and this is the total of these two different things. For example, if you know, like when you have like check homology and the Dehaene differential, we also have this kind of total complex. So this is just like something analogous here. So you have this double complex, and well, and you consider this total differential here, where you have to put this sign here, because when you consider these two differentials acting on this space, these differentials they commute. So you put this sign here so that this will scale to 0. Okay, so this is the complex. But actually, I'm interested in you can already see that actually the homology of this complex in degree 0 already give you like the functions of reduced space. But I also want to capture the Poisson. So, and for this, there is a very nice observation, which is the fact that this actually has a Poisson bracket. So this has a Poisson bracket we essentially defined by the duality between G and G, G star and G, and the Poisson bracket that you have here. So you define a Poisson a super Poisson bracket, so it's kind of graded. You have some, have to take care of the grading here. And so it's a super Poisson algebra with this, the bracket defined in this way. And there is something that's called here BRC BFE charge, which essentially this element here that, it's a function, somehow it's something here that lives here. And when you take bracket with it, it gives you the differential, okay? So in some sense, you're realizing this differential, you're kind of finding a Hamiltonian function to this differential here. So, this differential is the Hamiltonian vector field of this element here somehow, okay? And the fact that this satisfies this equation here because of the Jacobi identity for this Lie algebra, okay? You can kind of do this computation. And what I'm calling here in the BRST BFE algebra is actually what Constance Sternberg called the BRS algebra. It's like this guy with this Poisson, super Poisson bracket, and with this this derivation here that's given by this inner derivation given by this element. Okay, so there's this theorem by, this Constance Sternberg theorem, and also by Stashev, which says like, oh, okay, so the fact that you have this as this differential here, you realize it as an inner derivation. The Poisson structure that you have here goes to cohomology. So there's a well-defined bracket in cohomology. From here states two Poisson algebras here are actually isomorphic. So this is what I mean by homological reduction. So when you have like the regularity, the correct regularity, here you also have like this is isomorphic to the reduced space. So this is what I mean by homological reduction. So you find a complex whose cohomology, like here in degree 0, is isomorphic to something that gives you function in the reduced space. So this kind of algebra here is a replacement somehow for the reduced space. So because, like you take cohomology, you know about functions, but, you can simply go back and forget about the reduced space and somehow talk about the function of the reduced space without talking about the reduced space properly, because it may not even exist in some cases. But in the case of usual Hamiltonian reduction, it exists, and it's given. We have this statement. Okay. So I've explained like this direction. So we have like this differential graded Poisson algebra, which is this K with this derivation. And now I want to explain how we generalize this to this setting here. Okay. As I said, like this kind of this setting here is actually, it comes from a non-graded interpretation of the Hamiltonian reduction of the shifted cotangent bundle. So I will explain this now, but you see that there will be like a kind of one-to-one correspondence here when you have like this kind of graded action with a graded moment map on this shifted cotangent bundle. You translate it to this. Okay? So the way that I'm going to use this description mimics what I did here. Okay? So let me go like this setting here and how it translates to this setting here. Okay? So I don't know if you know, but let me talk about this shifted cotangent bundles. Okay. Good. Shifted cotangent bundles. So you consider a manifold M. The shift cotangent bundle of M is it's a degree 1 manifold. And what I mean by that is like you have like the shift of functions now. You see the functions on this manifold here as actually multi-vector fields, so sections of the exterior algebra of the tangent bundle. So, if you take some local coordinates for M, we can write a multi-vector field of degree P in this way, right? So you have like write like these partial derivatives here like in this way. So essentially you can see this as a polynomial algebra where you have like some odd generators down, because this guy here kind of anti-commute with itself. Like the product here is the wet product of vectors, okay? So by this, I only mean that the algebra functions is like this graded algebra. So I have some, besides having the usual functions, now I have some, some other elements that under the multiplication, they anti-commute, okay? Good. So, and there is a Poisson bracket on this kind of thing, which is actually the Scouting bracket of multivector fields, but it turns out to be symplectic. The formula for the bracket, this formula is essentially analogous to this usual Poisson bracket. So this bracket here is essentially defined by extending the bracket of vector fields. You extend it as derivation to multivector fields. And when you do that, and you write it in coordinates, you get this. And you see that this bracket is actually a symplectic bracket in some sense. Okay? So, good. So this is the shifted cotangent bundle. So let me talk about the Hamiltonian reduction of the shifted cotangent bundle. So you consider now a Lie algebra which is concentrated in degree -1 and 0. And you consider a map to derivations of this algebra. Okay, so kind of vector fields on this manifold here, they are essentially derivations of this graded algebra. Okay, and for this side, you see that the corresponding fundamental vector field -1 because I asked this map to preserve it. So this guy in degree -1 goes to something in degree -1. This guy in degree 0, it goes to something in degree 0. Okay? So, okay. So, but I want this action to be Hamiltonian. So what does it mean to an action to be Hamiltonian? It means that you have Hamiltonian functions associated to it. And I have a Poisson bracket here, right, in this manifold. So what does it mean for this guy or this guy here to be Hamiltonian, right? So you have like the corresponding Hamiltonians are a function for this guy because I want to write this guy here. So I want this Vm to be bracket with something, right? But this guy lies in degree -1. So here, and this bracket here is a bracket of degree -1. So I have to put something here of degree 0. And something of degree 0 is just a function. And something of degree 1 is just a vector field. Okay, so the Hamiltonian associated to this thing here is a vector field, and the Hamiltonian associated to this one is just a function. So you see that they're interpreting geometrical terms because you have some functions and some vector fields. Okay, so okay, good. So the definition of a moment map. So I just put everything together in a systematic way. So take a moment map for this action is a morphism. Here I include this odd, but you can forget about it. Of graded algebras that satisfy this condition here. I just want to say that when I take the bracket of two elements in the algebra, it goes to the bracket of corresponding constraints. Okay, so but actually, this maybe this I should call this a co-moment map somehow, right? But still, dually, you can see this map as a map of degree 1 manifolds. So you can see this map here actually generating a map between this shifted cotangent bundle and another degree 1 manifold. This guy here is just degree 1 manifold associated to this trivial bundle here. So you consider G8 star, right? So you consider this trivial bundle and you consider the corresponding graded manifold associated with it. It just means that you see like this guy as a base fiber in it, and so the generator of the algebra functions of this thing here is just sections of this guy with coefficients in functions on G star. Okay? So good. So just like it's good to have like this picture here for some statements. So okay, good. Let's see how I'm going time-wise. Okay, good. Okay, so this is what a Hamiltonian action in this graded context, okay? So what's the constraints to manifold, right? Now that you have, you can look at the map and see what you have. So let's do that. So the constraints to manifold, see here I'm using this notation of this corresponding, I'm taking the pre-image of 0, okay? Now you can forget about it and think that this is just this constraint manifold is defined in terms of the shift of vanishing ideals. So it means that I take the constraints in degree 0 and the constraints degree 1, and I span this ideal here inside the multivector fields. So it's a homogeneous ideal of this graded algebra, okay? And it has, okay, so, and the fact that this is a moment map implies that this ideal is coisotropic, so I have this condition, which is analogous to this one here, right? And as I said, there's a geometric picture for it. So we have this guy, constraints to manifold with, so here I should say that this C that appears here, this now is the vanishing the span of these degree 0 guys. Okay? Yeah. So this guy here, essentially this part here is associated to this, and this part here is associated to this. And this condition here actually implies that this distribution here is actually tangent to this level set. So what I mean is that you have something like that. You have this guy, which is this C, okay? And you have like this tangent distribution here, which is given by these other guys here. Okay? So geometrically, this constraints to manifold in M gives this data for you, which looks pretty much something that you want to consider as some reduction data, right? So manifold, and you have some distribution. So it's integral because the condition that this condition here implies that it's involutive. Yeah, so it implies that this distribution here is involutive. I think that only, because of this, I think that only on the constraints to manifold. Yeah, locally on the constraint, the constraint, but outside of, because when I want to look at some kind of quotient, like when you could have these ideals, you are looking, you look at something like that, at quotient, but this is actually some kind of limit that you do, and you consider this only on the submanifold somehow. So it's actually, you don't really, here I had away from the constraints to manifold somehow. So when you're looking at the what happened in the yeah, this is integral on the constraint manifold. Here, this is the correspondence. You see now. And I got this guy here. This map is essentially what's defining here. This action, which essentially distributes. So there is a correspondence like between an action and a map that's equivariant. So, and it's essentially given by kind of picture here. So you translate the Hamiltonian action in the shifted cotangent bundle in purely geometric terms in M, you kind of get this correspondence here. H here is the degree -1 part of this guy here. So you remember that this guy has H in degree -1. When you go to this side, this H is the guy that was in degree -1 here. And you can go, you can go from here to here and from here to here, okay? Good. So, and there's also something like related to the fact that in graded terms, what the meaning of this guy being a regular value of this map of graded manifolds, you can translate it in these terms here. And it actually means that this guy is a regular value of the map that defines this constraint manifold. So this is indeed like embedded to manifold. And the action is actually free. Along this action here is actually free. So when you do like, you can prove like this kind of relation as well. Okay? So the reduced space. So it's essentially the same as what happens in degree 0. We have, as I said, like here I'm looking only what's inside. I look at this quotient here, which essentially functions on the constraints to manifold. But now I think like in the graded setting, right? And now here I mean by taking the invariance with respect to the action. And there is also, here is a similar correspondence as in degree 0. So you have like this normalizer, but now the normalizer is taken with respect to this Coulton bracket, right? And you have like this kind of correspondence. So you go here, and then when the reduced space exists, you go here, okay? And there is this kind of degree 1 Marsden-Weinstein theorem that's due to Catano-Zambon in this paper where they discuss Poisson reduction in graded geometric terms. It says that if you start with this graded moment map, you know, for this action, and you assume this regularity condition, so this essentially here is something to guarantee that the reduced space, so the leaf space of C by this distribution here exists. So if you have this, then this space here that you construct is actually the shift cotangent bundle of the leaf space. What does it mean? Like it means vector fields on the reduced space. So it's a way of getting vector fields on the reduced space. Okay? So this looks pretty much like something that you want to take as reduction data for Poisson structures, right? You know, like this very general theorem by Marsden-Hatu, where you have like a constraints to manifold and distribution that satisfies something, then you can reduce. Okay, so this looks pretty much like structures, and a degree 2 function that satisfies this condition here. Okay, so this Coulton bracket of pi with itself is 0. Okay, good. So, like this corresponds with vector fields on the reduced space, right? And since you have like this correspondence here, a Poisson structure is reducible, so it goes to the quotient if only if it's a normalizer, okay? Since you have like this relation here. And so in this case, we have a corresponding reduced Poisson structure, right? Because if it's a normalizer, so you can consider the corresponding class here, and it defines for you a bivector in the quotient, okay? And it's, you know, it satisfies this condition because it's already satisfied its condition above, okay? But notice that for a bivector to induce a Poisson structure, since you take a quotient, right? When you go to, you know, when you go to reduced space, you take a quotient. For something to satisfy this condition on the quotient, it's enough that this guy satisfies this, because, you know, you're going to quotient out this. So, you know, it's okay for you to have like this kind of, you have this freedom here. So, and here, I mean like these weak Poisson structures that was considered by Liakovich and Sharapov, you know, which where, you know, like you have some Poisson structure that is only Poisson when you restrict to somewhere. So, and in Poisson geometry, we know this, for example, as quasi-Poisson spaces or things of this kind, where you have some, you know, the bivector that you consider is not Poisson, but it's Poisson up to something. And you know, like something that is the data of a Lie quasi-bialgebra or something like that. So this essentially, this weak Poisson structure, it fits in this context. Okay, good. So under this here, like, you know, okay, translated to this side. So what I mean by that is, what here? What's the meaning of this condition, which written in graded terms when I go to this side, right? Because everything is happening here. What about this condition here? And so this pair here, I mean the corresponding pair associated to a graded action. So I mean this pair here. So this pair will be said to be compatible with a Poisson structure if you have this condition. So the functions here, I mean the functions on M that restrict to functions that invariant, they are closed on the Poisson bracket. But now you can think of this Poisson bracket defining everything. But when we restrict, they are closed by the Poisson bracket on the submanifold. And this, you have like the annihilator of this distribution here is contained on this the distribution that is spanned by these constraints of degree 1. So if you're in the usual Hamiltonian case, this is actually an equality. So here see that there are quotients that is smaller than what you would quotient in the usual Hamiltonian case. So you are quotient out by contained in the gate of the action. This definition here is just spelling out what's the meaning of a Poisson structure in the normalizer of this graded ideal. Okay, so this is a translation of the condition. And so, and under this interpretation, the degree 1 theorem that I told you about, the degree 1 version of the Marder-Weinstein theorem, when you translate it, like when you put, like you turn like this Poisson structure on, the theorem here gives this generalized version of the usual Marder-Weinstein theorem. So you have like this guy, the action, and now you have like this equivariant map that take value here, and you assume that this pair is regularly compatible with the Poisson structure, so you are assuming this condition here. So this is essential reducibility condition for this Poisson structure, and this guy here is just, this other condition here is just something for the quotient to exist, right? And then the quotient inherits a Poisson structure. So this is essentially by following this correspondence graded and non-graded. So we start with the Hamiltonian graded picture, you translate and you see what the meaning in non-graded terms, and so this is essentially the way that you get this theorem here. So what's the corresponding homological version of this result now? How can you produce like the same, like the thing I started with, so like this differential Poisson algebra? What's it in this context here? Okay, so let's see. So the idea here is to consider this interpretation for this differential graded algebra that I told you about. You remember, like we like Poisson bracket, and if you like, you see, like if you put the glasses of graded geometry, you can see this as functions on this manifold here. Now you have M, so you have some other coordinates that are a bit weird because they anti-commute, but still you can see this as functions on this place here. And this actually has a Poisson bracket, and this guy here is just a function on this space. So, and this guy is just a homological vector field here. So there is this kind of other way of seeing this differential graded algebra, which is just like, you know, the algebra functions of a graded manifold with a homological vector field that knows everything about the reduction in some sense. So, you know, you change all the symmetries and then give like, you translate all the symmetries to this single Hamiltonian vector field here in some sense. So this is the picture that I want to use to obtain a Hamiltonian version of the other theorem. So the idea is to go through the graded picture. So because I obtained this by interpreting the Hamiltonian reduction of the shifted cotangent bundle. So I'm going to do homological reduction of the shifted cotangent bundle, and then I will get something related to this here. Okay? So in analogy with, so I consider the usual Hamiltonian graded Hamiltonian reduction data. And in analogy with this case, I consider this manifold here. So you see, it's directly analogous to this here. So the only point here is there's a 1 here. So never mind. The point is that the algebra functions of this guy here is now something like that. You have some symmetric powers here, of this graded algebra, and you're essentially doing what I did. So I'm defining the analogous of the degree, in degree 0, in degree 1. So I consider these guys here, and now I define this graded algebra where I have this new grading, where the grading is just take the difference between these two. And now this space here is actually bigraded. So before you had like a degree here that actually, when you define this, coincide with the degree that you already had, but here you have some internal degree. So these degrees, they are different somehow. So you have like this algebra is actually bigraded. Okay, so I consider this algebra with this additional grading. Okay, because now the grading are different. The other case, this grading coincide with the grade that I already had, but now I have some internal grades here. So I have two different gradings. So in the charge, in this way, analogous to the had in degree 0, and this satisfies this equation because of the graded Jacobi identity for this graded algebra. Okay, so you have like here I have the constraints, and here I have the structural constants of the graded algebra. Okay, good. So the homology in degree 0. So you see this guy here with respect to this grading, this guy has degree 1. And you can actually compute that the bracket, there's a bracket on this algebra here as well, because here I have a Poisson, the Scouting bracket, and there is also a bracket here that's given by duality between these two terms, but this bracket now has degree -1, okay? So, and I have this element here, which is the corresponding, the element that will generate for me the symmetries somehow. And so, and I have this theorem here, which I quoted from this paper by Alejandro Bonecchi and Zabzin in degree. Actually, the theorem there is more general. It's for brackets of degree n. I'm just spelling out the case where you have degree 1. So I should also mention this work by Yakov-Sharapov, where the ideas are so, there are some thing related to that as well, where the bracket has degree -1. So the homology of this guy in degree 0, but now you have additional grading here. So this is the homology considered with respect to the thing that I'm called total Gauss number, and there's an additional grading here, but this map is an isomorphism of degree -1 Poisson algebras. In other words, this homology here computes for you the reduced multivector fields. So this is the analogous of the, I could say like the Constant-Steinberg theorem in degree 1. So you have some homology that computes for you the reduced multivector fields. Okay, because this thing here is the reduced multivector fields. Okay, so a corollary of this, I'm running out of time, but okay. So a corollary of this is if you consider a Poisson structure that is maybe weak or not, like it will be reducible. So it's in this normalizer if you can find a cohomology class in degree 2 that satisfies this condition. So this guy here is something that goes to the corresponding class of pi on this quotient. Okay, so this is just an application of this result, right? Because if you have something that is here, you can consider the class, and you go back by this map, you have this pi, capital Pi that I wrote here. Okay, so this is just a corollary of this result. And it turns out that with this guy, you can define a Poisson bracket on this 0-0 cohomology. So because, as I said, when you have like bullet here, you have multivector fields. So, and this bullet computes the degree of the multivector fields. When you have C2-0, you have functions on the reduced space. And it turns out that with this co-cycle here, you can define this derived bracket. This derived bracket is a Poisson bracket. And actually, we have like this Poisson algebra is actually isomorphic to this algebra. So this homology with a dot here through this derived bracket construction also knows about the Poisson reduced algebra. So it knows about the reduced multivector fields, but it also knows about the reduced Poisson algebra. Okay, so you see, but there is two different things here. I have like this function Q, and I have this guy. So it seems to be like two separate things, right? So I'm doing first taking cohomology, and then I consider this pi And the question is, can I do like, can I, you know, like, can I put these two things together? Like, and this is what I wrote here, what I'm calling extended BRST BFE charge, actually is the fact that you can find an element which is actually a formal sum that puts together, you start with this Q that knows about the reduction data. And then you consider Y that knows about the Poisson structure. Then you can complete it in such a way that this equation is satisfied. Okay, so this formal sum satisfies this equation. And you know, if you know a bit about this LA infinite algebra, this, you know, this should ring a bell for you. So you consider this guy now, this kind of abelian algebra, and it turned out that this function here induces a homotopy Poisson structure on this space. And this is essentially by this Voronov construction of homotopy algebras, where you have like, you have some adjoint derivation, you consider a abelian algebra and a projector to this abelian algebra, you can use this element here to induce a homotopy Poisson structure here.
Maybe it's not a good idea to denote this like S infinity, because it looks like S infinity structure. Actually, this is a P infinity structure.
Yeah, maybe.
Paper by Voronov, you may find S infinity structures.
Yeah, it's called, you refer to scouting, right? Which is different. Maybe I should change the notation. That's right. Maybe, yeah, good. Thank you. But it's still like, the point is that these brackets here, they are derived brackets, right? And the first bracket is defined in this way, so it's the differential given by this first guy. The second bracket is defined in this way. So it's the derived bracket that I had considered before. And now I have higher brackets, which are given in this way. So here you have to put some sign, because this is actually related to this way that you related symmetric algebras to anti-symmetric algebras, this décalage isomorphism or something like that. So, okay, so, you know, I start with this function that knows about the reduction data, something that knows about the Poisson structure, and you can complete to get this homotopy Poisson structure. So now, you know, just to say that from this equation here, you can spell out what are the relations that you get between these terms. And for instance, between these terms, you get this relation. And you can do the computation by hand to see that you get this kind of up to homotopy Jacobi identity. So here you have like the usual expression for the Jacobi identity, and here you get something that is up to homotopy. So you have something that is a differential and a bracket of 3 elements. So this is really up to homotopy kind of thing. Okay? Good. So just to say, so and there is also identification of this algebra with some multivector fields on a graded manifold, on this graded manifold that I'm considering, and this shows this correspondence. So it's a kind of Weinstein-Lagrange neighborhood theorem for this Lagrangian submanifold, and we have this here. And this means that all these guys are bivectors on this graded manifold. And this, so this guy here is actually a formal bivector on this manifold, and this connects with this thing that people call P-infinite algebras, and also the zero-shifted Poisson algebras. Okay, so this guy is a formal bivector on this graded manifold. Okay, it satisfies this, you know, the bracket with itself is 0, and it's a formal sum. Okay, so now we get to the theorem. Okay, so, you know, I took like this graded Hamiltonian picture, I did homological reduction, I get this homotopy structure, now I translate back in non-graded terms. So if you get like this generalized, kind of generalized reduction data, you assume like the regularity that you need to consider the corresponding reduced space, and you get that this algebra here now have a homotopy Poisson structure where the brackets are, you know, like the proof is essentially following the path that I just showed you. You consider the corresponding moment map associated to this data, you consider this algebra that models the reduction, the graded reduction, you have some regularity that guarantees that this guy exists, and you consider the rapid brackets. Okay, so this gives the homotopy version, the homological version of this theorem. So this construction that I just showed you gives the homological version of this the result here. So let me move to some examples. I'm running out of time. So you can consider actions by DGLAs. So action by DGLA, so here you have like a differential on this algebra now, and the map that you consider actually respect a differential that's defined on derivations of multivector fields by the Poisson structure. So this guy here defines for you a vector field here. You take commutator with this vector field. You ask this map to respect this differential. Okay, and it happens that you consider a corresponding moment map. In this case, you have this condition. So you have action by Poisson vector fields, and you have this kind of relation between the constraints. Okay, so this guarantees to you that the Poisson structure is reducible, for example, because this is saying that the Poisson structure is the normalizer of the graded ideal. And so if you consider this guy and this guy, where this guy here, Aij, is just the and this induces the structure of graded algebra here. And just I want to say that Hamiltonian reduction for the Hamiltonian cases, the case that I'm showing you, you just consider this algebra with minus here, and then you get these two terms, this satisfies this, and this gives the constant Steinberg, usual constant Steinberg construction in this algebra. So just a particular case of the other case. So let me see. Still have some minutes. So Lie algebras. So this is one of the cases where the Poisson structure is not invariant. So action, an action on a Poisson manifold, but the bivector is not invariant with respect to it. Here I don't have these constraints of degree 0 that give the constraints to make restricted to anywhere. Higher terms, it doesn't square to 0. It's not true that in this case these we already square to 0, we have to complete. But still, you have something, a bracket that's defined only in terms of the Lie algebra data, somehow, okay? So notice here that I'm considering h equals to 0, so I don't have to restrict to anywhere. So there is a generalization of this case, which is like these quasi-Poisson spaces, which I consider now a Lie algebra. So in this case, I'm considering one of these weak Poisson structures because this guy is not Poisson, it's Poisson up to something. And it's this trivector that I consider that's part of the Lie algebra data. And now the charge induces a structure, so the first two terms are the same because the fact that this is a co-cycle for this only depends on the fact that this is a co-cycle here, so it's okay. But now I can say what's the first term of the next term, and something that depends on the trivector. And maybe you may have something else, but still, you have some homotop algebra, homotop Poisson algebra, which depends only on the bialgebra data, right? So one more minute. So and here, just me, I don't have much time, but and there is a way to consider this Hamiltonian quasi-Poisson space, which are group evaluated when we have a group evaluated, right? And in this case, if you have this, I don't have time to explain exactly what it is, but I am in the context of Alexev, Kozman, Schwarzbach, and Maiken. So if you have this, so they have this reduction theorem for these group evaluated moment maps, right? So this Marsden-Weinstein theorem for a group evaluated moment map, and applying the same ideas, I can consider a homological version of this theorem as well. So I obtain a homotop Poisson structure here, that gives for me functions on the reduced space, where now this moment map here is actually a group evaluated moment map. And so here I use, for example, this idea of taking log of a moment map to get a usual moment map, but now you have to change a bit the Poisson structure, but never mind, it works for this construction. So it's hard to write down exactly what's the Poisson, homotopy Poisson structure, but we still have it, okay? So it exists. So let me just conclude with some questions. So to understand the relation between what has been done in the graded setting, so I mentioned here mainly Safonov, Kalak, and Pridihan, that have worked a lot with this derived simplex geometry. And for example, there is this thing that they always say, and don't quite understand, maybe because I don't know enough about this language, but that Poisson reduction is Lagrangian coisotropic intersection. And if you look at their papers, you see that there's some, some similarities between what's happening here and what's happening there. But the point is that I don't know how to do the translation. But and something that they do there is like they study some equivalence classes of these shifted Poisson structures. So, for example, one shifted in their sense is like in correspondence with quasi-bialgebroids, for instance. So you could take a look at what are the equivalence classes of zero shifted, and could also look at quantization, because there are some theorems of Pridihan in terms of quantization of these derived things. So these are more questions for myself, and maybe they already know it, so just like wondering about what could happen. So something else is this complex that I've shown you in Hamiltonian reduction for the Hamiltonian reduction of this guy. You could do it for general coisotropic submanifolds of the shifted coordinate bundle, where now you don't have the constraints. So it's a bit more complicated to do that because, in the non-graded case, there's work by Hans Pridihan and Florian Schatz but you should adapt the arguments for the graded case. And it would be maybe this is just something that I wonder about. You could, using these ideas of Marco Zambon and Cattaneo in this paper with graded perspective for Poisson reduction. For instance, they obtain this very general theorem Mardin-Hattiu as press-simplex reduction of the shifted coordinate bundle. If you do that, some kind of embedding theorem of press-simplex manifolds, you could get some homological version of more Poisson reduction theorem following this path. So this is something just like some idea. And here, what's actually my main goal. I would say that I start to look at these kind of things because I want to understand actually this, which is the last point, which is homological coherent reduction. What I mean by that is like this is actually work in progress. Following ideas of Burstein, Cattaneo, Mehta, and Zambon, we have a correspondence between Hamiltonian reduction in degree 2 and reduction of exact Cohen algebroids in the sense of Burstein, Gautieri, and Cavalcanti. So you could go like you can perform this idea, you can apply these ideas of homological reductions on this side, and you can apply this translate to this side to get some homological model for doing Cohen reduction. So this is, this is my main goal actually, to obtain a homological model. So for example, a question here would be, what's the corresponding homotopy structure that appears on this side? So what's the homotopy structure behind Cohen reduction? It's a question. So this is actually, this question here is actually the motivation for doing everything in degree 1, because Poisson's geometry is in degree 1. Cohen structures are in degree 2, so we should understand what happens in degree 1 to go to degree 2. So at least we have some idea now how to treat this case. Okay, so that's it for today. Thank you very much.
Thank you very much for this talk. Are there some questions, some remarks?
Sure.
Construction presented looks very general. So my question is, have any particular explicit examples of weak Poisson construction and homological reduction?
Yeah, I would say that this case of quasi-Poisson spaces is somehow explicit. in some sense, because this guy is weak Poisson in terms of this trivector. This bialgebra data is this guy is a cocycle, guy is some do anymore, essentially given of the bialgebra data. So I think that this is, you know, like this is kind of explicit. You know, you can actually compute all the terms, but somehow the terms are defined by this data, because when you start to do the computations, you see that these terms, they will spread out somehow. They will.
Particular explicit example.
No, I don't have. I don't have in mind one. I think that the only case, for example, this case, where is it? This case for an action, but it's not like for all the terms. Like you stop in the second term. Maybe if you generalize this, for example, instead of having like a differential grade algebra here, you have like a LA infinite algebra acting, and you ask this to be up to homotopy. Maybe you have higher terms here. I don't know, but I don't have like one.
Because it looks like very small share, but
Sure, yeah, but yeah, I think that this is, yeah, this case here is the only, like, for example, this case is the only, like, the more explicit that I can get so far, I would say. But at least, like, and also in this case, for example, this case is interesting that in this case, there's in this paper by Alejandro and Bonecchi and Zabzin, they actually get something that's pretty similar to this. There's actually the exponential of some semi-direct product or something. So this is actually somehow very explicit. So this guy comes from some semi-direct product. So, but it's exponential. So it's still, you have all these infinite terms. But I'm getting this essentially the same formulas through a different path here somehow. But it's hard to get something like a closed formula. Yeah, I still, yeah, I would be happy to hear some ideas.
In that case, it's for Poissonic groups.
Yeah. On the dual group, and you do same direct product with the
You bring it back to the exponential and then you get the infinity.
yeah, and the terms I've checked, and the terms are essentially the same that are the same one that appears here. So
Because this is only part of this S infinity.
yeah, this is only part of the first two terms. Yeah, this one here defines the Poisson bracket here, for example. But it's already interesting somehow because the Poisson bracket here only depends on the bialgebra data. So, okay, so yeah. Okay, this is what I have to say about it.
Some other comments or questions?
Do you have any idea of what would be feasible conditions to like have some limitation in terms of like number of terms?
No, one thing that I maybe it's possible here is that you can prove that this is somehow quasi, you can find this kind of homotopies, right? So you could find something that is quasi-isomorphic to this structure and have finite terms. So, but you should, maybe here you should use some general theorem, you know, about like these infinite algebras, where you can construct this kind of, how is that called? Like these contractions or things of this kind. So you may, this is the reason why I was saying, for example, these equivalence classes here. Because you could like kind of put in the same equivalence class, you know, something that's very complicated, but it's quasi-isomorphic to something that's kind of simple. So, you know, maybe it's possible. I just don't know exactly how to do it.
It makes no sense to.
Sorry, did?
So it's not
Yeah. Yeah, okay, yeah.
Questions or remarks? So if not, let us thank the speaker again.
Thank you.